So students, welcome back, and so we'll be going to the third part of the lecture today, and most probably it will be the last one also. So we actually studied a lot of things till now, and so about a new set of numbers called complex numbers, how it can be represented, how we can add it, how we can multiply it, and even how we can divide it. And we studied about a special, a method of multiplication called conjugate multiplication, which is basically to divide. To do the division operation. Now, so let us continue from there. So we looked on how to divide, and so before that we looked on what conjugate is, and we understood that conjugate is what should we do to get the horizontal mirror image. So trying to get the horizontal mirror image, or the mirror image about the x-axis, or considering your x-axis as a mirror and trying to get the reflection. That is what conjugate is, right? So we already saw that. Now let us see a few things about quadratic equations. So I'm sure you have already studied what quadratic equations are, so let us look a little more into that. So we studied so we all have already studied about quadratic equations, and let me give an example. So one example will be x square plus 4x plus 4, and you all know how to solve this, right? It's splitting the middle term method. Sum is 4, product is 4, so it will become x square plus 2x plus 2x plus 4 is equal to 0. Then you take common x, it will be x plus 2, and you take common 2 from here, it will be x plus 2 is equal to 0. So you write x plus 2 together in the bracket, and then you write whatever is outside the bracket. X plus 2 is equal to 0, and then you see that it comes like this. Now if you just multiply this whole thing again, if you multiply x plus 2 into x plus 2, you will get this equation. And then after this, you write the roots are x is equal to minus 2 and x is minus 2. So yeah, it is having the same roots. So this same roots. So what we see, is this method won't apply every time. That means won't be for example, now since it was easy numbers, 4 and 4, it was fine. But suppose you had numbers like 3 by 2 and 4 by 5 and all in the quadratic equation, how would you solve it? It will become difficult. So by using splitting the middle term formula, so what we or method, so what we would do is we have a general format, a formula in which if you directly apply the values, you will get a root. So I'm not showing you the proof of that formula because it is because I doubt whether you will be able to understand that now, because already everything that you're studying is a new concept. So if possible, if we get time, anytime later in some other chapter, I'll try to show it to you. Okay. So this is the general form of a quadratic equation: ax square plus bx plus c is equal to 0, where provided a is not equal to 0. Remember, this is whenever you say quadratic equation, you should also mention this condition where a is not equal to 0, because if a is equal to 0, this term goes, then it becomes it becomes a linear equation. It doesn't become a quadratic equation. Quadratic equation, you should always have x square. So you should always, whenever you write this, you should also mention this condition. Many people forget this condition, even I forget it sometimes, but this is a very important condition to say that it is quadratic. Okay, so let me take the condition away now, just to make space for me to write. So this is our quadratic equation, general formula. Now the formula for the root is x is equal to minus b plus or minus. So one root will be plus and one root will be with minus. That is why plus or minus comes. B square minus 4ac whole divided by 2a. I know it is a long formula, but by time you will get used to it. So x is equal to minus b plus or minus root of b square minus 4ac divided by 2a. So so one root will be x is equal to minus b plus this thing in the root and then 2a, and another root will be x is equal to minus b minus what is under the root by 2a. So that is why this, so writing it together, that plus and minus I have written it in one line. So this is the general format, and we'll use the same thing, and we'll see whether it works for the previous example. So the previous example was x square plus 4x plus 4 is equal to 0. Now let us apply that. If the roots were minus 2 and minus 2, right? So let us check it. X is equal to minus b plus or minus root of b square minus 4ac divided by 2a. So according to quadratic, this is according to quadratic formula. According to quadratic formula, x is equal to minus b plus or minus root of b square minus 4ac divided by 2a. So x is equal to minus b is 4. So minus 4. Here it will not here plus or minus. Not. You should write the minus under the plus. Okay. So plus will be plus or minus, and so minus 4 plus, first I'll take x1 first. So it will be minus 4 plus root of b square. B is 4. So b square is 16 minus 4 into a is 1. A is the coefficient of x square, so it is 1. So 1 into c is 4 whole divided by 2 into a is 1. So 2 into 1 is 2 itself. So let me solve that, and what I get is minus 4 plus root of 16 minus 4 into 4. Oh, it's basically 16 minus 16. 4 into 4 is 16. So 16 minus 16. Oh, so it's basically 0. That makes it more easier. So it becomes is equal to minus 4 plus root 0 is 0 by 2. So this is minus 4 by 2, and if I simplify it, this will become minus 2. So you see that we get the same. Now what will be the next root? The next root will be the same thing. The next root will be the same thing with the minus in between instead of the plus. So instead of this plus, I need to put minus, and I will get the next root. So if I put like that, it will be minus 4 minus 0 divided by 2, which is again minus 4 by 2, and the answer is minus 2. So you see that by using this quadratic formula, you can find for any number, whatever be the number in the quadratic equation, you can find the roots. Now we have studied about imaginary numbers, so let us come to that concept now with this. So I told you that Heron of Alexandria, then and Euler and Rene Descartes, they all had the problem in solving equations, and that is one issue that everyone had. That is why complex numbers even were made with the concept of I. So suppose this is our equation, x square plus x plus 1 is equal to 0. If suppose this is our equation, now we know a is 1, right? A, so remember our general formula is like this: ax square plus bx plus c. So here we know a is 1. Okay, 1 minute. Yeah, a is 1, b is also 1, and we know c is also 1, right? Okay, so anyways, so if I'm taking this away, so this is our equation. Now if I ask you to find the roots, how will you find it? Let us use the quadratic formula. So x is equal to minus b plus or minus root of b square minus 4ac divided by 2a. So let me go on. So we know that a and b and c are all 1 only, right? So this will be minus 1 plus or minus root of b square is 1 square 1 minus 4 into 1 into 1 whole divided by 2a. 2, okay, 2a. A is also 1. 2 into 1, that will be 2 itself. Now this will be minus 1 plus or minus root of 1 minus 4 divided by 2. Now this will be equal to minus 4 plus or minus root of 1 minus 4 is minus 3 divided by 2. See, now like Heron of Alexandria, Rene Descartes, and Euler and all, we have also come to the same issue. We have root of minus 3. Now how are we going to solve it? Now, but like them, we don't have issue now. We have the complex numbers and imaginary numbers. So let us use that. So minus the root of minus 3i will be minus 3 into I, sorry, 3 into I, right? I mean, sorry, root 3 into I. So minus root of minus 3 is equal to root 3 into I, right? Root 3 into root of minus 1, which is basically root 3 into I. So let us use that concept now. So this will be minus 1 plus or minus root of 3i by 2. Wonderful. Now let us take both the roots. So this is a general formula for x. So my x1 will be minus 1 plus root 3 by 2, and my x2 will be, second root will be minus 1 minus root 3 by 2. Wonderful. So so this also this is the fundamental there is a theorem called fundamental theorem of algebra, and what that says is basically what is the maximum degree of each equation, that much roots will be there. That is, now we know this is a quadratic equation, so maximum degree is 2, right? X square, maximum degree is 2. So there will be two roots. Suppose we had a cubic equation, that is, cubic equation means it has x cube in it. So what happens? The maximum degree is 3. So there will be 3 roots. Suppose it is a linear equation, that means x to the power 1. Then since the degree is 1, we will have only one root. For example, x plus 3 is equal to 0. Maximum degree is 1 only here, right? X to the power 1. So what happens? How many roots are there? X is equal to minus 3 over. See, only one root. So in quadratic equations, we can have a maximum of 2 roots, and in linear equations we can only have one root, and cubic equations we can go for a maximum of 3 roots. So this is called a fundamental theorem of algebra. You just have to understand the concept of this one, and just remember that how much number degree you have, that many roots you will have. So I hope you are clear in using this quadratic formula to find the roots. I know the formula is a little long, but if you just practice the questions, and you will be able to understand it, or remember it. I hope you have understood about quadratic equations and how we can use imaginary numbers also in that. So now let us, I was told you right, that in the beginning, that I'll be proving something of trigonometry, or one formula or two formulas of trigonometry, with this complex numbers concept. So let us move on to that. Trigonometry. So now we come to the point where we all were waiting for, or at least I was waiting for. That means I told you I would establish the relationship between trigonometry and complex numbers. So we already understood that there is some relation, because we already saw z can be written as cos theta plus I sin theta. So of course there is trigonometry in that. But now, first, let me draw my unit circle anyways. We all start with unit circle. Okay, that is not a circle. My unit circle. Then let me draw my argent plane. Not quite enough. It should be around the center. So perfect. Okay, almost perfect. So this will be my imaginary axis, and this will be my real axis. Or x and y. I mean, if you write x and y, you should also know that in your heart that it is real and imaginary. That is all. So let this thing be there, and I told you that if I have a equation like this, I mean, if I have a not equation, I'm sorry, if I have a vector like this, and if this is a complex point, if I multiply it with j, what happens? It gets rotated like this. It gets rotated it gets 90 degree rotated in the anti-clockwise direction. Now, if I multiply it with minus j, what happens? Or leave minus j. If I multiply it with 2j, what happens? Again, it gets rotated by 90 degree, but double the size. 2j, double the size, right? So it will be like this, double the size. Now, what happens if I multiply with minus j? It will come here. It will come down. Instead of rotating anti-clockwise, it will rotate clockwise and it will come down. So we know that j. Okay, so I say okay, I use the value j, and now why I use j is because I usually use the term j. You can use I also. It doesn't matter. You can use I. So I is the mathematical term or preferred term. So if you use I, same thing. If you multiply with minus I, it becomes like this. So we know that multiplying by I makes it rotate. Whatever be the value, multiplying by I makes it rotate 90 degree. But that is I. But so when I multiply with 2i also, it rotates by 90 degree, but double the size. What happens if I multiply it with 2 plus 3i? What happens? It cannot go to full 90 degree because it is not just I, it is not just 3i, but there is a real number also with it. So what happens? It gets rotated, of course. Whenever I is there, it gets rotated, but it gets rotated by some angle, theta. And see, this 2 plus 3i, if it is if is equal to z, we know that this thing we can also write it as modulus z angle theta, right? Polar form of writing it. This is the argument, remember. Now this theta is this theta, this theta is this theta. So and there's a way to find the value of theta. It involves the way to find theta is equal to tan inverse b by a, and you won't see you don't know, you have not studied inverse trigonometry. That only comes next year, so I don't want to tell you that. It will confuse you a little more because you have not studied inverse trigonometry. For now, just understand there is a way of finding theta, and using that angle theta, we can see how much it rotates. If it was only I, it gets rotated by 90 degree. But if it is a full complex number, a plus bi, it doesn't get rotated by 90 degree, but some other angle, depending on what the theta is. Now, if you understood this much, you have understood actually a lot of things. I mean, you have actually understood understood the crux of what I'm going to tell you. So now, suppose Usmita comes to me and tells me, sir, how to find sine of 75 degree. And she asked me how to find sine of 75 degree, and I am like, wait, I know sine 30, I know sine 45, I know sine 60. What is sine 75? And I forgot to take my calculator, and my mobile battery also went down, and I'm thinking, and there's no other way. So what I can do is I can write this sine 45 sine 75 as sine 45 plus 30, right? Sine of 45 plus 30 degree, sine of 45 plus 30 degree, sine 75 degree, right? Now using this methods of multiplication in complex plane or in argand plane, I'm going to show you how to find it. So let me take this thing first of all off. Okay, because that is not there in our question. So first let me draw sine 45. So we all know what is the value of sine 45, right? Sine 45 is 1 by root 2. We know cos 45 is also 1 by root 2. One easy angle. It is one easy angle. So let me draw sine 45, and I will draw using this color. So this is sine 45. This is 45 degree. Perfect. Now we know that we know that if I and suppose I want to rotate this 30 degree upwards, okay, anti-clockwise. I want to rotate it 30 degree anti-clockwise. How can I do it? By multiplying by some complex number, right? I should multiply with some complex number that gives me angle theta, and then I can rotate this thing 30 degree. Okay, let me draw a perfect line. Then I can rotate, I use another color, then I can rotate this thing by 30 degree. This will be 30 degree. Okay, so to rotate by 30 degree I have to multiply by some complex angle. So it will be like not some complex angle, yeah, some complex value. So what will be that complex value? We know that this is, first of all, this is a unit circle, and unit circle we know that we can write it as, we can write z is equal to a plus ib, right? And at the same time we can also write it as cos theta plus I sin theta. So we know, so z1, our 45, or I will call it z45, z subscript 45 is equal to cos 45 plus I sin 45. Angle is 45 degree, right? 45 degree, because radians are also there, so we should mention degree. So let me rub this thing off. Okay, and I will move it a little up. Okay, so now what about set 30 degree? See, if I multiply, if I move this, to rotate this sine 45, so not sine 40, to rotate this vector, to rotate this vector into 30 degree anti-clockwise, I should multiply it with this vector, right? If I multiply it with this vector, this thing will get rotated. The final answer will be here, right? If I multiply it. So let me try that. So that will be, so I should know what is the 30 degree complex number also. So 30 degree complex number is set 30. I will call it set 30 is equal to cos 30 degree plus I into sine 30 degree. Okay, now if I multiply them both, I will get this angle. Let me take that. So if I multiply them both, I will get the final answer here. I will get the final answer here at this point, right? Now what is this angle? See, if I take the middle one off, you will understand. What is this angle? 45 plus 30 degree, that is 75 degree, right? Because this was my 45 degree and this was my 30, and again I added 30 degree, so 45, I'm sorry, this was my 45 degree and I added 30 degree, and so I get 45 plus 30, 75 degree. So to get 75 degree, I only had to multiply complex numbers of 45 degree and complex number of 30 degree of a unit circle, okay, of a unit circle. Do you understand? Now I don't know whether it's easy for you, but it might feel a little hard. Don't worry, this is not in the portion, this is not in the syllabus. I'm just telling you for I'm just telling this for your information and to make you understand what is actually happening. So if I multiply these two values, let's see what we get. So it will be, remember this, okay, set 45 is cos 45 plus I sin 45, cos 30 is cos 30 plus, sorry, set 30 is cos 30 plus I sin 30. So if I move it, okay, or I'll draw it in another page, so it will become set 30 or set 45 into multiplied by set 30 will be cos 45 degree plus I sin 45 degree whole into sin 45 degree, sorry, cos 30 degree plus I into sin 30 degree, and that will be equal to cos 45 into cos 30. So cos 45 into cos 30, or I will write it directly for you to understand. So cos 45 is 1 by root 2 into cos 30 degree. Cos 30 degree is 1 by 2 plus cos 45 into I sin 30. So cos 45 is again 1 by root 2, sin 30 is root 3. Oh wait, cos 30 is root 3 by 2, I'm sorry, cos 30 is root 3 by 2 and sin 30 is 1 by 2. This is root 3 by 2 and sin 30 is into 1 by 2. Then I sin 45 into cos 30. So I sin 45 is, this into I, and I into sin 45 is 1 by root 2 into cos 30, that will be root 3 by 2 again, and then plus last term I sin 45 plus I sin 30, and I is I square, so it will become minus, this plus will go, then sin 45 is 1 by root 2 into sin 30, that will be 1 by 2. So now what will be the answer? So the answer will be 1 by root 2 into root 3 by 2, that is root 3 by 2 root 2 plus 1 by 2 root 2 I plus root 3 by 2 root 2 I plus 1 by 2 root 2. So let me group the I terms together. So it will be first I will group the real terms together, so it will be root 3 plus 2 root 2 plus this term 1 plus 1 by 2 root 2 whole into I into this term plus this term, that will be 1 plus root 3 divided by 2 root 2. So now I have A plus IB format. See, now do you understand? Now if I take the if I take root of A square plus B square, I'll get the modulus Z. Now why I showed you this is, even if you without even having a calculator, I am able to find what is the value of sin 75 degree, or you can do this for any angle. Now let me show you a general form of doing it. So a general form of doing it will be Suppose, so if I have if I have an angle alpha and if I have an angle beta, and if I need to find the angle alpha plus beta, so how to combine them both, or leave alpha and beta? It is confusing, right? Let me take, if I have an angle x and if I have another angle y, and I have to find the complex, the angle. Suppose I have sine x, suppose I know sine y, and I need to find the sine of x plus y. How to do it? Let's take in a general format. So first I will write, so cos x plus I sine x plus cos y plus I sine y, right? This is equal to cos of x plus y, we know. So RHS I will write later. Let me solve with LHS first. So it will be, this will be equal to cos x, let me group the real terms together. So this will be cos x plus cos y, real terms, cos x into cos y, and let me put the sine term, the imaginary terms together. That will be plus I into sin x sin y. Now this is and then, so it will be I square, when I multiply. I'm multiplying this, okay, not adding it. So when I'm multiplying it, it will be cos x cos y plus I square into sin x sin y. So this will be my real part, because my I square will become minus 1. This I square will become minus 1. So this will be my real part. Okay, I think this is a little, okay, I think this is a little crowded here. So what I was trying to say is, I need you also to take a pen and paper and do this, because it is difficult for me to show it in this tab. I'm trying my best. So this will be cos x plus I sin x into cos y plus I sin y. So what will be the real terms? The real terms will be this into this plus this into this, because I into I will be minus 1, right? So you just open this, just open this thing, and you will get cos x cos y minus sin x sin y, because minus will be I into I is I square, so I square is minus 1. So that is how this minus comes. Then what will be the imaginary part? The imaginary part will be cos x, let me use another color. The imaginary part will be cos x into I sin y and I sin x into cos y. So it will be plus I'll take common. So cos x into sin y, I is already taken, so cos x sin y plus this term sin x cos y, I am already taken outside, so sin x cos y. Now does this look any similar to what you have studied? If we look carefully, now what will be the RHS? Okay, before that, what will be the RHS? The RHS will be, we need to find sine of x plus y, right? So I will take the complex number of x plus y, that will be cos x plus y plus I into sin x plus y, right? This is my complex number. Now when we equate a complex number, we know real number should be equal to real number, imaginary number should be equal to imaginary number. Now look at the real number. The real number here is x, real part here is x cos x plus y. What is the say equal real part here? Cos xy minus sin xy, right? And so we studied cos a plus b is equal to cos a cos b minus sin a sin b. See, now we got that without by hearting the trigonometric formula. We can get this now. Now imaginary part is sin x plus y. What we got it here? The imaginary part here is cos x sin y, sin x cos y, or sin a cos b plus cos a sin b. It's just, it just interchange, it's the same thing. So we see, so by just, by complex multiplication, we are able to even derive the trigonometric formulas that we actually studied. So why I showed you this is not there in your portion. Why I showed you this is to make you understand. Just to make you understand. Now always remember that, whenever you equate a term, when we say, okay, that I'll show you in another page. When we say one complex number is equal to another complex number, that means a plus bi, to say that it is equal to c plus di, a should be equal to c, real part should be equal, and the imaginary part should be equal. That means b should be equal to d. Then only we can say it. So it is using this principle that we said that the real part is this part, and we got it same, and the imaginary part is also this part, we got it same. Because we know trigonometry, now we know that it is actually the same thing. So I hope this has made you think that, imaginary numbers are just not imaginary, as Rene Descartes has said. It is not some imaginary concept. It is, even though it is called imaginary numbers, even though it is called complex numbers, it is actually a real thing. It is real as any other number. And how important it is, because see, in trigonometry it is a very important factor. I mean, I is a very important factor. At the same time, in wave in the maths involving waves, I is a very important thing. As I told you before, also in electrical engineering, I is one very important thing with which many things. So all electric lines, and we see the post and all is designed with respect to this term I. So as I think this is enough for today. So there's a lot of things covered. Please watch the video again if you have a doubt. At the same time, write and see it. Please do not just look at the video and assume that it is understood. Please write and see whatever you have, the lectures, when you hear, and when I do these proofs, do it by yourself, try it by yourself, and see where you go wrong. And when you go wrong, correct it, and then you will learn it. So I hope it is understood. If there's any doubt, do contact me, and soon we will go for the next chapter. Thank you.